Hello everyone. In this video, I am going to share with you the technique to find integrating factor, and the method which we are going to target is inspection method, and this method is usually comes under the topic of non-exact differential equation. So we are going to learn how to find integrating factor first, and then using it we will solve the differential equation. So before starting, what we are going to do is let us see some important result which are going to help us a lot to handle such equations. So the point number one is that usually whenever you see this expression d of xy minus y d of x, or you will see this expression y times d of x minus x times d of y, anything can be in the front, but the point is when we are having this x with dy and y with dx and there is a minus sign, then there in such questions there is a scope of using inspection method. So with this expression we cannot write in terms of derivative, we need something to be multiplied with it. Let's say 1 is 1 by x square can work with it, 1 by y square can work with it, 1 upon xy can work with this expression, 1 upon x square plus y square can work with this fraction, and one last one is 1 upon x square minus y square. Means these four expression can work with this, especially the x dy minus y dx. And how it will work, because when you are writing it in this model, it is a quotient rule of something. What is that? It is actually the quotient rule expansion of derivative of y by x. And so wherever we can see this thing, we can replace it by dy by x, which will further help us to find out the solution. So once you identify 1 by x square is working, it will help you to write it into dy by x. If this expression is working with y square, if it is y square in the denominator, then y dx term should be in the front. So it can be done by adjusting minus sign over there, and it can be further written as a quotient rule of x by y. And if it is working with x into y, so you must be observing in the numerator we are having the same expression, but when the denominator is changing, our d form is changing. So it can be written, when product is there, it can be written as d of log of y by x. If x square plus y square is in the denominator of the same expression, it can be written as a tan inverse formula. And if x square minus y square will work with the same expression, it can be written as d of 1 by 2 log x plus y by x minus y. So while solving problem, we can see that how it going to help us. And apart from that, sometimes if you see x dy plus y dx, when plus sign is there, we can replace this expression as a d of xy. So here I do not need to multiply anything to write in terms of derivative, but yes, in some of the problem this expression can also be utilized or can be used for inspection method questions. So wherever you see x dy plus y dx, with the help of product rule, it can be written in d form. So you must be observing in all these expression I am transferring this dx dy model into a derivative of the function of xy. And one more expression is very useful in these questions, that is whenever x is with dx and y is with dy, and if 2 is there, you can write down this is nothing but derivative of x square plus y square, because x square derivative is 2x dx, y square derivative is 2y dy. Or if even 2 is not there, only sometimes in questions 2 is not there, only x dx plus y dy is there, so this 2 can be adjusted on other side and can be written like that. Even one, in some of the cases it's not only in x and y, sometimes if you see the quotient rule or the product rule with some another functions, like let's say in this eighth formula I have written y e x dx minus e x dy upon y square. How I can rewrite it into the derivative form? So it means it is a quotient rule of u by v form, where u is ex and v is y. Like you can say y square, y constant, derivative of ex is ex dx minus ex dy. So that can be done. So these are few useful or important results which are going to help us. And after that, I would also like to share with you that during this process of finding integrating factor and multiplying the expression, we come across something like this. Means we are going to come across some integral. So we will see that what kind of expressions or what kind of functions can be integrable. So always remember, when you see dx and you are integrating, it always give us x. This is very rare. When we see dy, it can be integrable, so it can be written as y. Even if you see dx can handle all the function of x. Let's say in one example, if you see x dx, which you have already, I mean, you already used this. This is x square by 2, and even y. So these are the simple cases, the single variable. Now, in during this problem solving, you may come across these expressions. This expression, it means whenever you see d of some function of xy, if it is integrable, it means the answer will be xy. If expression is d of x square plus y, or you are integrating, it can be written as x square plus y square. If you see d of y by x, you are integrating, it can be written as y by x. So the same model can be applicable. In fact, it can be further extended. How? If you're observing your integration is working with xy, d of xy, then if you see any function in front of it, it will always be in terms of the same model. If it is xy function, so it should be, all functions should be product form, and you can follow the same integration formula over there. Like these last two cases, I have taken a special situation. Even you can see here, you are integrating d of x square plus y square. So if x square plus y square in the denominator, it is something like that. You are integrating something and there is a divided by, you always put a formula of log of this expression. So you just have to see the model, and you just have to cross check what kind of expressions are direct integrable. So these are all direct integrable. And let's see with the help of some examples that how we can find out. I will begin with this first question, wherein my first step is to find out the integrating factor, and with this inspection method, and then we will solve. So usually in the inspection method, what is our process? Inspection method is the process wherein we group the terms, and then we write down in terms of derivative, and then we integrate. That is a grouping, regrouping, or readjusting. Now here in this question, you all spot that x dy minus y dx term is here, right? And this side I am having dy term. And you know that if we want to integrate, first of all, I can't write this expression in d form. It need any of the five formula which you have, which I discussed in the beginning. So here I can see that dy can handle e to the power y, but this is something which it cannot be integrable. So dy is integrable with y function only, not with x square plus y square. So you can identify a one point here, that if this x square plus y square is removed, the question can be handled. And this side x square plus y square in the denominator can be handled. So I spot my integrating. Means you have to do some kind of rearrangement, and you can spot the integrating factor. So here integrating factor is 1 upon x square plus y square. Why? Because when you divide both side, you will multiply the both side by 1 plus 1 upon x square plus y square, and this side you are having, then it will be divided and it will come into only d of y times dy. Now it can be further written as d of tan inverse y by x from the formula which I shared with you in the beginning, and here you are having e by dy. So the step 1 is, first you have to spot the integrating factor, second is you just multiply, and third is write down in terms of d, and the fourth step is just integrate on both sides. So when you integrate on both sides, what do we get? We get this integration and d will go away, and we left with only tan inverse. In this case, we left with tan inverse y by x is equals to, here we were having ey integration, so integration of ey is ey and plus constant of integration. So that become our solution. Now let us see another example. Example number 2. Here means in few example I have taken up this expression, but this expression will work with any 5 of the variety of indicating factor depending upon the other terms. Like here in this question, I am spotting this expression x dy minus y dx. It cannot be written in d. It need any 5 of the functions which I shared in the beginning expressions. So here we can see dx is there. So we can find out this y square can be 1 upon y square can be integrating factor y, because y square is not needed. I need to divide this by y square, and y square, when I divide in this side, the front two terms, these two terms can be written in d model. So I spot my integrating factor as a 1 by y square. So when you have a 3 terms and this kind of expression, the third term can give you a clue of integrating factor. So here I got a clue of integrating factor 1 by y square. Why it is clue? Because y square is not working with dy, it is not dx, not integrable, but it will work on this side. So my question is going to move ahead with this 1 upon y square. So when you multiply 1 upon y square throughout, this y square will get cancelled, and we can write down this is equals to d of since y square is in the front, and by using the quotient rule, this term should be the front and this term should be later. So I can do a minus sign and then write down y by x by y. You can write like that, and here we are having only integration of dx because y square get cancelled. And when you integrate both sides, what we will get? We are going to get here minus that was the expression x by y plus d of y is equals to just a minute, no, it was d of x equals to 0. So after integrating, this d and integrator will go away, you left with only x by y, and this side integration of dx is x and constant of integration, so that become our solution. So usually in this method we have to first spot the right integrating factor, and then we can further rewrite it into d model, and then we can integrate on both sides and get the solution directly. Let us see one more question. In this third example, what we can see here, we are observing that x dy, let me make it correct. So here you are observing this expression is I want to change this question here, just a minute. Let me rewrite this question number third as x dx plus y dy is equals to 2y x square plus y square dy. Just let us take some variety. When you see x dx plus y dx, what we can do? I can write down this expression as d of half of x square plus y square, alright, and this side you can write down 2y x square plus y square d of y. Now let us see some grouping. Here this side, right side, I am having dy is there, it can only integrate y function, so this batch is not needed. So it is going to help me to decide a integrating factor, and I can see that when the model is of d of x square plus y square, 1 upon x square plus y square can work on this side, and when you will divide, it will removed from the right side and your expression will be in a integrable mode. So what we can do, our integrating factor is spotted, that is 1 upon x square plus y square, and when you divide on both sides, you are getting this thing, and this side we are having 2y, it will get cancelled. So both side is needed to take, so this get cancelled, and we are going to get here integration 1 by 2 d of x square plus y square divided by x square plus y square, and this side we are having 2y dy. So yes. So is it integrable? Integrating both side? Yes, this is integrable. This is integrable with respect to x square plus y square. This is integrable with respect to y. So when this is integrable with respect to x square plus y square, d upon something divided by the same expression is not anything, just a log of that expression. Log function will work over here. Here you are getting y integration is y square by 2 and then constant of integration. So that become our answer for this question. And similarly we can see the fourth question. Now here let me open this expression to get idea. When you open, you are getting 2xy square with dx. I'm multiplying both this side dx and this side y, and there's a plus sign. You're getting y dx minus x dy. Now what we can do, as soon as I have shared with you, if you spot this term, you will get an idea that in any five of the variety of indicating factor can work over here. And I'll see my third expression, this expression. In this expression, I know this expression cannot be written in d terms, the derivative term, apart from having any of the five, without any of the five options. So my this term is integrable only for x, so this y square should be removed. So y square, when you removed, only when it will be 1 upon y square, and 1 upon y square will work on this side, so integrating factor is spotted. What is that? Integrating factor is 1 upon y square, and when you are multiplying both side by 1 upon y square, basically you have to multiply integrating factor to the expression, and we will get this y d of x minus x d of y upon y square is equals to 0. And this expression y square cancel, and we are having 2x dx. So let us write down this side 2x dx, and we are having plus here, and this is y dx minus x dy by y square, so it is a quotient rule of dx by y. So this is a quotient rule of dx by y. And now you can integrate both sides. When you integrate both sides, so 2, it is integrable with respect to x, this is integrable with respect to x by y, and constant of integration. So this way we can solve, and we can also find out the integrating factor. And let us see one more question here. I'm increasing the difficulty level. So here we can't spot in this manner. Let us simplify. When you multiply, you are getting 2xy square. We are having dx plus y e to the power x dx, and let me transfer this term on the other side like this. So let me see which group can be make. E to the power x and e to the power x is here, so let me make a group of these two terms, and think of the minus sign is there, so quotient rule can be created. So because it is mixture of ex and y, so what we can see, come to the side, third term which is in the front, dx can only integrable with respect to x. So this y square need to be removed, then this part can be integrable. And this side I need something. What I need? I need y square. So yes, integrating factor is spotted. What is integrating factor? 1 upon y square. So usually whenever you have a three terms, whenever you get any special pair which I shared in the beginning, that special pair of writing, it can help you that variety of indicating factor using that options, and looking into the third term, it can be spot, I mean you can identify the indicating factor here. So what we can do, multiply both side by indicating factor, and when you multiply both side by indicating factor, you are getting 1 by y square plus y e to the power x minus e to the power x dy divided by y square is equals to 0. Here y square get cancelled, and you can see that u by v formula. What is u by v? This is v square, this is v, u is e to the power x, so derivative of, you can say, e to the power x is u and y is v. So when you find out the derivative, you're getting y square, y derivative of e to the power x is e to the power x dx, minus of the formula, e to the power x constant, derivative of y is 1 times d, so it is correct. We can write down it as a e to the power x upon y, and this side we are having this term. So yes, now it is integrable. You can integrate both sides. This side you can integrate d of e to the power x by y. Yes, this is integrable because it can be written in d terms. This is integrable. So when you integrate, you are getting this term, and this will be e to the power x by y and constant of integration. So we get the answer. Let us do this question, sixth one. Here I have taken the four terms, so let us figure out how we are going to solve it. So we are going to write down this term as, let us open this expression. So that will be y cube with dx plus y dx plus x y square dy minus x dy is equals to 0. So I am going to group, because here I have taken two terms. I am going to make a group of these two terms and group of these two terms, and let us figure out that whether something will work or not. This side you are having y cube, and here you are having dx, here you are having plus times xy square dy, and we can write down y. Let us make a group of these two and group of, because I spot this y dx minus x dy, so sometimes it always give you a hint. Make them together. Here let me take it out y square common and see what happen inside. Inside you are having y dx plus x dy. Yes, this can also be written in terms of d, and we got this identity. I mean, we got this expression that y square is not needed here. Why? Because y square is here, and you can write down this as a d of product, and here you are having y dx minus x dy is equals to 0. I can't write the D model here. I can't integrate y square with respect to xy. So this element need to be removed from here, and this can work on the other side. So this is a process, student. Whenever you are having anything like that, you just have to figure out what will work, what will not work. So we have to look into all the terms of the expression. We cannot only think one term at a time. This term can work with any of the five variety, but here my term on the left side, this is only working for a product, so this y square need to be removed. So we are getting an idea that what is integrating factor. So integrating factor in this case is 1 by y square. So what happened, whenever you are having this y square in the front, this d of xy, when you multiply with 1 by y square, here you are having what was that, y dx, y dx minus x dy upon y square. Yes, now I can write down this term as a derivative of x upon y. This side y square cancel. We are having derivative of product. So now it is integrable. So integration of d of xy is xy. Integration of d of x by y is x by y, and that is constant of integration. So this way we can find out the answer, means we got the solution. Only this important step is when you need to figure out what is the integrating factor. So here I'll say what is the integrating factor. Integrating factor in this question is 1 upon y square. This is the integrating factor by inspection method. Let us see one more question. So let me open the other term. When we open, we are getting x times dy, and here you are getting x cube y square d of y. I know that y dx and x dy can be written as d of product, and this side I can only integrate y square, so it can only give the product form. So x cube is not in the need. So x cube is not in the need in this side, but here I can only utilize product form. I can't say alone x, I can't say alone y. So not alone x, not alone y is working. So what should be the appropriate integrating factor? This x cube is giving me hint that if I multiply by 1 by x cube and y cube, so it can be of the model of x by cube. So yes, let us see whether it is working or not. So it is going to work. So integrating factor is 1 upon x cube plus y cube. When 1 upon x cube plus y cube, you are getting this x cube plus y cube can be written like that. Here you are having x cube y square d of y upon again x cube plus y cube. X cube get cancelled, y square will cancel with 1, so it is a correct integrating factor. Reason being, we can write down this expression as a product form. So you have to look into the integrable pattern. This is integrable with xy model. This is integrable with y model. So we got an high hint from here. So we got that this is d of xy. It is nothing but xy minus 3. And this side you are having d of y. All get cancelled and we left with. Now it is integrable. So integrate both sides. When you integrate, xy to the power minus 3 is minus 2 by 2 plus dy by y is log of y and constant of integration. So that comes the solution. So I'll take the last question here. Let us see this last question. What is that? X dy minus y dx. Now again I am spotting this term. Let us figure out what can be taken common from here. So I know that here x to the power 4. So let me take it out. What is the maximum power? I can take it out x cube from here. I can take it out y from here. And here we are having, when you're taking x cube and y, it is x dy plus y dx. Okay, let us first see the situation. Here it is x cube y. This can be further written as d of product. This can be written as, this is, just a minute, this was x times dy. Okay, so this is x times dy minus y times dx. Let us figure out what can work. Here I know 1 upon x square can work, 1 upon y square can work, 1 upon this x into y will work. But right now if I see my right side term, here the product can work, means xy can work. So y is there, I need 1x. So if I write down this as a x square and this is xy, then this become something which I need to remove from here. So I got a hint. What I got a hint? I got a hint of my this integrating factor. Just a minute. I got a hint of the integrating factor. Here integrating factor is x dy minus y dx. Here it was xy d of xy. So yes, I am going to decide the integrating factor. Integrating factor of the current question is 1 upon x square. When 1 upon x square is multiplied both sides, so you are getting this dy minus y dx upon x square. This side you are having x square, xy d of xy get cancelled. This expression can be written as, this is a quotient rule, u by v square, v dv, and that's it. So you're going to write on that is equals to d of y by x, and here you are having x into y with d of x by y. So let us cross check. Is it integrable? Yes, it is integrable. Is it integrable? Yes, xy can be integrable with respect to a product. So when you write down integrable, the answer is integration of d is y upon x. Integration of xy with respect to xy is xy square by 2 plus constant of integration, and that becomes the answer. So I hope you have gotten the idea how to handle this method of inspection and to find out the integrating factor, and then further can be solvable by using the integrable technique.